Good morning, everyone, and welcome to our very last Zoom of the quarter. So today we are going to spend some time talking about some of the medical advances that have been developed as a consequence of our understanding of antibodies, how they work, how to make them, what they do. And so the nice thing I think about this section is that it is dependent on a lot of things you've already learned about. One thing I want to just remind us of is these 4 types of adaptive immunity that you will have covered in the prep. So the adaptive immune response can give you sort of antibody-based immunity, but we kind of categorize it differently depending on whether or not the antibodies were generated by your body or whether you received them passively. So did you have to actively generate antibodies or did you passively receive them? And then was that as a result of a natural event in the course of most human life, or was it a medical intervention, usually an injection of some kind? So in the category of sort of naturally occurring things where you might have to generate your own antibodies, in this instance, we experience some antigen, might be a pathogen, bacteria, virus, toxin, or could be something like pollen that we have an allergy to, but that antigen enters the body and we produce antibodies against it. And we also produce typically memory cells. And so this usually results in long-term immunity. Passive, naturally acquired passive immunity is when we receive antibodies during the course of in gestation or during breastfeeding from mom. Now, on the other hand, we could develop our own antibodies or receive them as a result of a medical intervention. So we could be vaccinated or we could be provided with antibodies that have already been created. The difference here, again, just like with the naturally acquired immunity, is that the active one results in longer term immunity. Okay, so let's see if we understand all these different categories. What protects newborns that lack their own mature adaptive immune response? What type of immunity do they have? Write that into the chat. You have to say whether it's natural or artificial and whether it's passive or active. Great. That's right. So this is natural passive immunity, and it's conferred by the antibodies provided by our moms, either transplacentally in utero or in breast milk during breastfeeding after birth. And so this is an important immunity. Of course, it is not long-term. So there is a point at which these antibodies expire. If you're being breastfed, then you get sort of regular reinfusions of them, although only IgAs, not IgGs, as long as you're being breastfed. But there is it's not for months or years once the source has gone away. All right, what's the goal of vaccination? What type of immunity are we trying to establish? What's the goal of vaccination? What type of immunity does that provide? That's right, Heather. Yes. Obviously, it is an artificial intervention, so it's artificial. And because we're providing the body with the antigen and we have to make our own antibodies and consequently also typically our own memory cells, this is considered artificially acquired. Active immunity does typically last for a long time. Now, if we compare vaccination to natural exposure, the difference is that, you're avoiding some of the risk of whatever that natural exposure comes with. So you're using an antigen and you're generating an antibody and memory response, but you're avoiding whatever that risk is of the natural exposure, whether it might be whatever the toxin does, whatever the infection the virus might lead to whatever damage the bacteria does, et cetera. Okay, so this is true in Ebola outbreaks towards the end of the last century. There was a controversial therapy developed that involved transfusing convalescent donors' blood into newly infected patients. What was the hope? What type of immunity was this hoping to provide? Transfusing blood from a convalescent donor into a newly diagnosed patient. Okay, yes, that's what you're hoping, is that the antibodies of the convalescent donor are going to protect the newly infected patient. So what kind of immunity is this providing them? Yeah, artificial, passive. You didn't have to make your own antibodies. It's not a natural thing to be transfused with someone else's blood. And this actually, while very controversial at the time, has become more routine in different kind of contexts. It does seem to be, and is the basis for some post-exposure prophylaxis that uses antibodies as a protection against an active infection. Okay, so one of the very important things that you needed to get from the prep for this section is what the different vaccines are, their pros and cons, how they work, etc. When we think about vaccination, of course, an important thing is to understand the difference between the primary and secondary response, being that the primary responses are first exposure, secondary responses, subsequent exposures, and both the time that it takes to respond, the effectiveness of that response, the robustness or titer levels of antibodies is better the second time around, or the third, fourth, and fifth time. You want to make sure that you understand the definition of herd immunity, that situation where at least 90% of the population are immune, which protects the remaining 10 or so percent. And then you want to know from this part that what the types of vaccines are. So let's start with that. Put into the chat any of the vaccine types that you learned about when you were doing the prep for this section. Okay, good. Excellent. Wonderful. Okay, so we have inactivated whole agent, attenuated whole agent, toxoid, subunit, and nucleic acid. Good work, guys. Well, those are all the ones, and we're gonna review them today. All right. Can you use antibiotics to fight a viral infection? Yes or no? Good. So why not? Raise your hand. The answer is no. Many of you are writing that, and that's excellent. Raise your hand if you can explain what's the problem. Why is this not a good option? McKenna, go ahead.
Does that have to do with the Gram stain results and the peptidoglycan and the cell wall?
It is. That is absolutely on the right track.
Okay.
Does anyone want to sort of tie into that great start to this answer? Why can't you use antibody? Oh, Aria, go ahead. What else would you like to add?
The viruses don't have any of the structures that the antibiotics target.
Exactly, right. And that's what McKenna was getting at too. She was talking about how, we learned about Gram staining. It's relevant to whether penicillin is going to be useful, which sort of speaks to that bigger point, which is that antibiotics target things like the cell wall or sometimes the ribosome or, other features of cells, but viruses aren't cells, so they don't have those features. Another way to sort of think about it is that cells are metabolically active, and the things that are being targeted are things that metabolically active organisms have or need, and viruses don't, right? So this is an important thing that once you know it, you can't really unknow it, but until you know it, then it doesn't seem silly to go to your doctor and ask for an antibiotic treatment for a viral infection. It's only once you know it that you're like, well, that just is never going to work. Can you vaccinate against bacterial infections or just against viral infections? If you're not sure, you can use a question mark. If you are sure, put your answer in, but do put in something. Can you vaccinate against bacteria or just virus? I mean, I will sort of provide the broader context of, yeah. Okay, keep going. I'll just wait for I'll wait for you to weigh in. I'll stop talking for a moment if I can. Great. Okay. So before I directly answer this, I would like you to put into the chat the name of a vaccine or vaccines, if you have multiple that you know of, and we'll just see if we can answer the question, if the answer's in the question. So what vaccines have you received or do you know about? Like against, okay, flu, so COVID, Gardasil, Varivax, Tdap, Shingrix, MMR. Yes, okay, and anthrax. Good. So what you'll notice is, as I'm reading these out, is a lot of virus ones, obviously, COVID and flu and MMR, but also some bacteria like anthrax and DTaP, right? All of the things in the DTaP shot are bacterial. Diphtheria is bacterial, tetanus is bacterial, and pertussis is bacterial. So the answer is both. You can vaccinate against both. Now, it's easier usually to develop an effective antiviral vaccine. Usually it's easier. And that has to do a little bit with what your options are. So we're going to kind of look through this again when we talk about the types of vaccines. But think about what the options are that we wrote into the chat. Attenuated whole agent. That only works for viruses. You can't do that with bacteria. And inactivated whole agent, also just viruses. Subunit, very commonly done for bacteria, can also be used for viruses. Nucleic acid could really be used for either, honestly, but is most commonly done for viruses. So there's more options, different methods for doing viruses. They're just easier to vaccinate against. They have fewer antigens. It's easier to pick one that's going to be useful. And you can use a whole agent, which you can't with bacteria. All right. Now, we're not going to go through this again because we just did, but you want to make sure that you understand the 4 types of adaptive immunity and be able to provide an example. And so I'll just say that there's a slide here you can use in your study, which is kind of better defining these types, which is naturally acquired active immunity resulting from infection, naturally acquired passive immunity when you receive antibodies transplacentally or in breast milk, artificially acquired active immunity, which is when you vaccinate someone, and artificially acquired passive immunity when you provide injected antibodies. All right, so now let's talk about vaccines. Right, vaccines are typically quite effective. They vary, of course, so they're not always 100% effective, and some of them are only like 20% effective, but most of them are pretty good. And they are most effective when you use them. It's also worth noting that they're not historically the only or even the most important factor in disease reduction. And so we've talked about this before, how historically the biggest impact on contagious illness was achieved by cleaning up water, basically providing clean water. While vaccines and antibiotics and other medical interventions have been very helpful and important and remain important, if you're starting from a place of no access to clean water or good food, then there are some other things you might want to do, at least in parallel, to try to increase public health. And so we can sort of see again this example of typhoid cases where cleaning up the water reduced typhoid cases a great deal. And this other sort of view of it where we look at kind of total death rates in children, and we see that when vaccines were introduced, they certainly made an impact, but before then there were a lot of other interventions that had made quite a dent as well. So are diseases like polio, measles, tuberculosis, and whooping cough still a problem, yes or no? Yeah, they are, right? So in wealthy countries with access to vaccines and clean water and other things, then this really has not, it does not have a big impact. Like you don't typically worry, like living in Everett or Linwood, that your kids are going to die of measles or whooping cough, or that you're going to catch tuberculosis. That's not a typical concern. But in the world as a whole, there's still a lot of infectious disease, and it tracks a lot with resources. Okay, so just a sort of, sobering kind of statistic, infectious disease primarily kills children globally, and it's a high death toll still, okay? Measles in particular is very effectively prevented by vaccination. That's probably the best thing you can do for measles. All right, now we also have the situation that I think is pretty prominent in our minds. New diseases arise all the time, and they really don't have any respect for borders. And when they're new, having a lot of resources and wealth can mitigate their effects, but they don't spare people just because they're, living in a situation where there's not a lot of viruses usually. So with new viruses, the problem is, of course, there's no prior exposure, so there's no herd immunity. So the death tolls and the impacts tend to be higher in the beginning. There's no vaccines. Treatments may be limited or not available. We maybe don't even know which treatment to offer in the beginning. Respiratory viruses are particularly problematic because they can transmit so easily typically. And of course, there's this problem of previously controlled pathogens being able to mutate. So with that, let's talk about vaccines. So there were types of vaccines that you listed in the chat already. These were the ones that came up. I'm just going to give you a couple of examples that you don't have to memorize, but just so that you kind of feel connected to the things you know. So the attenuated whole agent is where the entire virus particle typically has been passaged through usually chicken cells is the most common way to do this, until it mutates sufficiently to still look like itself. It's still antigenic. It still has the surface proteins of the original virus, but no longer has the ability to cause disease in people. And if you read the history of how this is done, which is one of the earliest techniques, it's quite fascinating, and it was really more of an art than a science, especially for the measles one, how that was developed and sort of finding that fine point where it's still what they'd say about it is passing it through chicken cells through many generations so that the virus would still look human enough to be recognized by our immune system, but chickeny enough to not cause a disease in people. So attenuated whole agent is what's used in the MMR shot against measles. It's also in one of the versions of the polio shot from the 1950s. And it's also one of the forms of flu is an attenuated whole agent. This is the one that's administered nasally, so most of us have probably not had this one. The inactivated whole agent is where you take the original agent and you just usually heat or some other form of denaturing, gentle. You denature it sufficiently that it's incapable of causing disease, can't even replicate, but it looks exactly like the original. And so this is the basis for one of the other polio vaccines developed in the 50s, the Salk one, which is a little bit safer to use. And it's also how we make the flu vaccine. That's usually the one you get administered. Subunit vaccines, where we take a little piece, and this is much more common for bacterial vaccines, although you can also do it with viruses like hepatitis. Vaccine is a subunit vaccine. We take a little piece, usually a little protein, sometimes a complex carbohydrate, for example, a piece of the capsule of the causative agent of pertussis. Toxoid vaccines, you take the endotoxin or the exotoxin that's primarily responsible for the symptoms of the disease. You gently denature it so that it looks like itself, but is incapable of doing anything to you. And these types of toxoids are very effective, and it's what's in the tetanus and diphtheria shot. And last but not least, nucleic acid vaccines. Fascinating thing about this is that until recently, these were not commonly used in people. They were very effective against West Nile virus in horses, but have become the mainstay for COVID-19. Okay, so toxoids are the heat-killed exotoxin, and my animations are coming up backwards. Sorry about that. Toxoids are the heat-killed exotoxin. How does attenuated differ from inactivated whole agent? Raise your hand if you'd like to answer that. I already discussed it, but see if you can remember and repeat or re-explain that. How does attenuated whole agent differ from inactivated whole agent? Raise your hand. Or you're welcome to put your answer into the chat. Anything that comes to mind that's different between these two guys. Aislinn, go ahead.
Oh, there we go. The attenuated aren't killed, they're just changed.
Yeah, that's a good way of putting it. They're not killed, they're just changed. They're changed enough so that they can't hurt you, but they can still replicate. That's right, Katie. Whereas inactivated has been sufficiently denatured that it's no longer capable of even replicating and cannot cause any disease. How does a subunit differ from the whole agent? Raise your hand or put your answer into the chat. How does a subunit vaccine differ from whole agent? Aria, go ahead.
The subunit, you just use a small piece of the virus or bacteria that is antigenic, but a whole agent, you use the whole virus or bacteria.
Right.
Or virus, I mean.
Yes, exactly. So this is a small piece. Example might be a polysaccharide from a capsule or a spike protein from a virus rather than the whole pathogen. Okay, now nucleic acid vaccines are really interesting. What would you say is different between these and other vaccines? Can anyone speak to this? Raise your hand or put in anything that comes to mind into the chat. What's a nucleic acid vaccine? How does it differ from other vaccines? Heather says they use genetic material. That's right. What happens next? So in goes the DNA or RNA. And for the COVID-19, it's RNA. What does your body do with it? Yeah, that's right, Sunday. Your body takes that genetic information and uses it to make the protein that's encoded by the genetic information. And so it creates the antigen. So the way to think about this is, in typical vaccines, you introduce the antigen into the body and then you make antibodies against it. But in a nucleic acid vaccine, you introduce the instructions for the antigen, then the body makes the antigen and the antibodies. Yeah. Good. Okay, so now let's talk about like why we use different types. What's the situation there? Of these different types of vaccines that we've talked about, which one is typically the most effective? Yeah. Typically the most effective is going to be the attenuated whole agent. Why is that the case? Raise your hand. Why is it that the attenuated whole agent is the most effective? I'm just going to cold call some people from the chat, and remember that when I do that, you're always welcome to pass. But I'd just like to hear your reason for choosing the answer you did. Let's start with Renette. You said attenuated, which is accurate. What was your reason for choosing that one?
Well, I said that it's an intact viral particle, so it would elicit the strongest immune response.
Yeah, it's intact. And that means both that it's like got all of its antigens, but also that it is capable of replicating. So the attenuated whole agent contains all the original antigens, or pretty much. I mean, there's going to be a few changes after its passage through the cell culture, but it has a ton of the original antigens, and it's going to elicit the strongest antibody and memory response. Now, what is the risk of this type of vaccine? Because it is not without any risk. The risk is usually low, like 1 in 2 million. But what is the risk? Mutation, right? Mutation leading to what? Mutation leading, because it's able to replicate, so it's capable of mutating. Yes, back mutation to the virulent form. It mutated to get to the current harmless form. So there's a chance it could mutate back to the virulent form. That's absolutely right. And it usually is about a 1 in 2 million chance. Okay, so what that means is that this highly effective vaccine is best used in a situation where the risk of the disease is greater than the risk of the vaccine. Right? The disease is sufficiently concerning that you're much more likely to get the disease naturally than you are to get it from the vaccine. But 1 in 2 million times you'll get it from the vaccine. Now, subunits, completely safe. That's a major pro, right? Because it isn't a pathogen. It's not capable of replicating. It's absolutely, it's just a little spike protein. It's a little piece of a polysaccharide. It's not capable of making more of itself. So you're not going to get the disease from it. But consequently, what's the downside to this? Why wouldn't you choose this all the time? It's less effective because there are fewer antigens for the immune system to recognize. That's right. So you don't have all of the antigen. You have to kind of pick your antigen. And what if you picked wrong? Or what if you had that rare person who just didn't have a B or T with that antigen specificity? Then that vaccine's not going to work for them. Okay. So when we think about like our choice for when we decide to create, generate, and widely deploy a vaccine, we're going to do it for things that have, a widespread impact and are dangerous. Things like smallpox and measles are very easily transmitted. Smallpox is very lethal. Measles has a great impact in children. And it's obviously not as lethal as smallpox, but nonetheless, lots of kids die from measles. And you're extremely likely without a vaccine to spread measles. It's extremely infectious. And we've talked about why antibiotics are ineffective against viruses, right? Because they don't have the right structures. We've talked about whether you can vaccinate against bacteria or just virus. So what about this? Is it enough to vaccinate just one time usually? I mean, it does depend on the vaccine, but usually the booster shot is required, right? Because when you get that booster, it creates even yet a larger population of memory cells and boosts your ability. But also, do memory cells live forever? Do they last forever? No, we obviously know that that's not the case, because if you think about how often you have to get your tetanus re-upped, it's every 10 years. I mean, if it was a lifetime shot, you wouldn't have to do that. So we need boosters to replenish or increase the pool of memory cells. Okay, now what about this? Why, we don't have a vaccine against the common cold, but when you do catch a cold as a kid, it's not like you're protected forever. Like I remember as a kid, I would get sick like every month for 10 years. It felt like I literally went through probably 100, colds. And what is the reason for that? Why did it keep coming back? Many different strains is the primary reason, right? What we call the common cold is actually not one thing. It's much more diverse than even the flu. There's 200 strains of viruses, more or less, that can cause the cold. So if you caught one, then you might be protected against that one for a decade or something, but there's going to be another one. So there's a lot of different cold viruses floating around all the time. And yes, they also are continually mutating. All right, a much bigger problem in terms of the flu, this annual flu shot we talked about before. What's the reason we need one every year? Yeah, that's right. Antigenic shift, antigenic drift. The flu is this perfect storm that leads to the possibility of relatively rapid mutation. So there's always new strains of flu arising, always. Why is it that children and the elderly are typically at higher risk for things like the flu and other diseases? Why is it that children and the elderly are at higher risk of things that your adaptive immune response is normally able to fight off? Yes. Good. Great answers, guys. And I particularly like Katie's answer because it's specific. So she says weaker or naive immune system. Children have a naive immune system. Their immune system is pretty strong, but it's naive. It hasn't seen very many things. So children are often at risk because they have no natural immunity to stuff. They've never been exposed to it before, unless they've been vaccinated. And the elderly are at risk because even if they've seen it before, their memory cells might be on the way out. Now, an interesting thing happened in 2013. I don't know if you remember this, but there was a strain of flu that went around.
I have a question really quick.
Yeah, McKenna, go ahead.
So with the memory cells like on their way out, is that why shingles can be so bad? Like for certain seniors?
Yeah, that's part of it. Although the more important part is the latency of the virus, which is a big contributing factor too. The virus tends to hide out and then resurfaces many, many years later when your memory cells are low. So yes, and it's typically hiding out in cells that are not easily detected by T cytotoxic cells because the virus is not actively replicating, it's not actively producing antigens. That's the primary reason.
Okay, thank you.
You're welcome. Great question. All right, guys. So in 2013, there was this strain of flu that went around. And you know what the concern with the flu is always that it's going to be in 1918 all over again. And in 1918, the flu was very typical in the sense that the people most impacted were old people and very young people, and like people who were in their 20s and 30s were the best protected. But there was this inversion that happened in 2013, where actually the elderly population was more protected from the flu than everyone else. And the people who were most impacted were typically in their like early 20s. How do we explain this? What's going on here? Aislinn, go ahead.
Possibly because it was a strain either that had already been introduced or was similar to one.
That's exactly right. As it turns out, the particular strain that was circulating was one that had shown up and infected a lot of people like, 40, 50 years prior. And so the elderly population had some immunity to it. They had been exposed before, and the younger people were decades too young to have ever seen this strain before, and they were the ones impacted. Okay. So some of the other things that we want to remember, and we'll just briefly kind of touch base on, is when you're making a vaccine, and if you're doing it against viruses, then you're going to have to culture the virus. And we have a number of methods for culturing viruses that would allow us to generate large scale amounts of them for vaccine production. What are our options when we go to culture a virus? Put that into the chat. You want to grow viruses. How can you do it? Think animal viruses primarily. And if you don't remember putting the question mark, it's totally legit. Yes, you can grow it in an intact host, which is not usually very inexpensive, and it's not great if it's a human host. You can grow it in cell culture, and you can grow it in embryonated chicken eggs. Okay, and the one thing you can't do is grow it the way you grow bacteria and just put it into culture media. That will not work. This is really commonly done. This is by far the least expensive, most high throughput method. All right. What was the one thing? And we've talked about this before, so I'll just remind you that there is a risk, therefore, of vaccines developed this way for people who have egg allergies, in which case you need to find the egg-free version, which you can usually find. It's just more expensive to make, and there's less of it usually available. Okay. Now, antibodies are generated by vaccination. That's the goal. But understanding how antibodies work has led to a number of other interesting advances to things that maybe we wouldn't necessarily originally have thought would be helped by this technology. Mylin, what's your question or comment?
I'm going back to the vaccines that are, if you have an egg allergy, it's difficult to get the vaccination, but not all vaccinations, am I right? They don't all contain an egg.
That's correct. They don't all have eggs, and that's why if they do, they'll ask you, do you have an egg allergy? And if you do, then if it's available, they'll offer you an egg-free version. But not all vaccines out the gate are developed in eggs. It's just very common.
So was it developed differently then if it's not?
Yeah, usually the egg-free ones, there's a couple ways to develop them. The most common sort of second strategy, if you're not going to do it in an egg, is to do it in cell culture. And so that's totally feasible for many things, but it is a bit more expensive. cell culture is just harder. It requires more, it's higher maintenance, right? It requires more babysitting. And so, but there's lots of viruses that have been grown that way. And typically there'll be batches of these types of vaccines, but often in just lower quantities because they're more maintenance to develop and more cost.
Okay, thank you.
Great question. Okay, so we talked about this a little bit, or we kind of illustrated this a little bit with Lab 8, that knowing how antibodies work has allowed us to develop a plethora of antibody-based diagnostics, from diagnostics for contagious disease all the way to things like fertility and pregnancy and drug testing and whatnot. But even just in the field of medicine, where we're looking at infectious disease, it's really useful to have an antibody-based or a rapid antigen test to find out if someone has a particular disease. And in addition to that, there's a couple of interesting therapeutics that are antibody-based that have proven, or at least promised, to deliver some of the benefits and the effectiveness and the safety that people originally imagined, like hundreds of years ago, when medicine was starting to become more scientifically based. And so there's this idea that was, that's old, of a silver bullet or a magic bullet that would destroy a disease but not harm people, because historically a lot of medicines that are effective against infectious disease are somewhat toxic. As an example, syphilis used to be treated with arsenic, and syphilis is a bad disease. It's a terrible way to die if that's what happens to you. It sometimes gets cleared by your body, and some people have a horrible ending. But so arsenic is a poison, but syphilis is bad enough people were using it to try to cure their syphilis. You can develop a version of that, Salvarsan, that's less toxic, but it's still not perfect. But what antibodies offer potentially is a way to do exactly what people first wanted to do, what they first hoped and imagined would be possible, which is specifically take out a pathogen without harming the host at all. And so one of the fields where this has potentially great consequences is cancer, because cancer is not an infectious disease usually, but it is one where you're kind of up against the same problem. You're fighting your own cells, your bad cells. So they're a lot like other cells in the body. Anything that you use to kill them is likely to be harmful to the rest of the body. So what do we have to resort to? Poisons, chemotherapeutics. But antibody-based treatments could potentially target specific, unique, minute differences between cancer cells and the regular rest of the body, and take those out specifically and leverage our own immune system against them. Another place where they've been particularly effective is in some autoimmune disorders, things like Crohn's disease. And of course, also post-exposure prophylaxis, so a variety of diseases, and to venoms and other things that aren't microbiological, but nonetheless harmful. Now, just a quick conversation about how we make antibodies. This isn't the only method, but this is a commonly used method for decades. It's very effective. Making monoclonal antibodies in mice. And monoclonal is a term that just means that the antibody that you end up using commercially is one specific antibody that's pure, like it's just that one antibody. There's thousands of it in the vial, but it's all the same exact antibody. So it has exactly the same antigen specificity, and therefore its performance is extremely predictable. So how do we do this? Well, we take advantage of the mammalian immune system. Mice and rabbits and llamas and all the mammals out there have the same type of immune system that we do, which is that if you inject them with something that they consider to be foreign, they will make antibodies against it. So for mice, which were chosen for a lot of reasons, partly because they're a lot easier to grow in large quantities as compared to, say, a llama, you inject the antigen that you want to generate an antibody against into a mouse, and its B cells will become activated if they're specific for that antigen. A lot of B cells are in the spleen, so we harvest the spleen. This unfortunately is not a survivable event for the mouse. And we take all the B cells out of the spleen and we put them in a suspension and mix them with a cell culture line of cancerous B cells. So these are B cells that have two changes. They no longer make antibodies. And they are immortal. They live forever, which is different than your B cells. Your B cells have a particular lifetime. So we mix them together and we cause them to fuse one of these cancerous B cells called a myeloma with one of these regular B cells with an antibody. These hybridomas are then separated out one by one into individual little dishes, fed so that they grow into clones where each one is unique. We select for the hybridomas, killing both the non-fused spleens and the non-fused myelomas. So the only thing left is this hybrid cell that has immortality, but also one unique antibody. And then we test each individual well until we find the one that makes the antibodies we like the best. And then we grow them forever. Simple enough, right? It's pretty amazing. And this works really well. And you can use these antibodies for all kinds of things. You can use them in ELISAs. You can use them in various kinds of test kits. You can use them in rapid antigen tests. You can use them to do a variety of research projects in the lab. Okay, so you inject the antigen, you get the B cells out, you fuse them together with the immortal cancer line, you select for the hybrids, and then you basically just characterize and keep the ones you like. And this you do not have to memorize, but just to give you a sense of what a powerful tool this is and what kinds of conditions that are really recalcitrant to other treatments, or where the treatments are almost as bad as the disease, and where these monoclonal antibodies have been revolutionary, is, for example, in organ transplantation, you're up against the body rejecting the organ. So you can suppress some of the T cells using an antibody against part of the T cell receptor for those kidney transplant patients. If you've ever known anyone with Crohn's disease, it's a degenerative disease of the GI tract that's terrible. And it's probably an autoimmune disease. And so you can make this antibody against tumor necrosis factor. That's a cytokine that's thought to be part of the whole systemic inflammation problem. And you can, in some people, alleviate their disease. There are certain types of cancers, such as leukemia, very difficult to treat, where an antibody has been shown to be effective. And another type of cancer that you've probably heard of, breast cancer. There's lots of variants of breast cancer. One in particular called HER2 positive breast cancer is well treated with this, with the trade name trastuzumab, which is also known as Herceptin. So again, no need to memorize this, but just to understand that it's extremely versatile and powerful technology and is likely to continue to yield lots of benefits as we move forward. Of course, you can use it for diagnostics. And in that case, you remember when we did the ELISA, you needed your controls, your positive and negative. So you want your diagnostic test to be sensitive enough so that even if whatever you're looking for is present in very small quantities, it's still going to turn out positive. Okay, so sensitivity is important. If it's not sensitive enough, we can get false negatives where someone really is infected, but we don't know because the test turned negative, right? And we want it to be specific so that it's not cross-reacting to other things. So if someone isn't infected, their other antigens are not sufficiently similar that they would trigger a false positive. Just to kind of give you a sense of some of the early ways this understanding of our immune system was used, in that for sure you have been experienced in some degree. This was developed a way to test for tuberculosis. So guinea pigs that already had tuberculosis were then injected with Mycobacterium tuberculosis. Again, the site of injection became red and swollen. Does this sound like a test that you've had? Yeah, right. Pretty much. If you work in healthcare, I worked in the decon department in the basement of a hospital, never handled patients. I still had a test for tuberculosis, which was the skin test. Now, this is a little tricky, right? First of all, we don't inject Mycobacterium tuberculosis whole in people. We use like an antigen that's part of the tuberculosis bacterium, but can't give you tuberculosis. But if you've been exposed to it before, you'll have antibodies, and that will cause inflammation at the site. That's how it works. It's pretty simple. If, however, you haven't had tuberculosis, but you have grown up in the country, primarily this was done in Eastern Europe, where you were vaccinated against tuberculosis, then you'll also come up positive on the skin test. So you have to do other things to determine what's going on. And antibodies are used in ELISAs, enzyme-linked immunosorbent assays, where an antibody is linked to an enzyme. And then if the enzyme is present, then the substrate, which is normally colorless, is changed to a colored product. So we've done this, and presumably you remember kind of how it works, but what does the primary antibody in the ELISA do? What does the primary antibody bind to? It binds to the antigen, that's right. So you have a sample, patient sample, and you want to know if the antigen's in there, is the virus in there, is the bacteria in there, is the toxin in there, whatever it is there a pregnancy hormone in there, what's in there? The primary antibody is going to bind to the thing you're looking for, okay? And then the secondary antibody binds to what? It binds to the primary, right? And then the enzyme is attached to the secondary so that you can add a substrate and find out if the antigen is there, right? If the enzyme is present, it's going to cause a colored product to appear, and that will tell you that the antigen is there also. So here's a little cartoon of that. And again, you've done this, so this should be relatively familiar. There's 6 million versions of the ELISA. This is just one example. We put the antigen on the well, we add patient serum, and we find out if there are antibodies against it, and we have our secondary that reveals the presence of that. Or we put our antigen on the well and we add primary and then secondary to find out if there was antigen in the serum. There's a couple different ways to do this one. We can also do the sandwich one, and this is the basis of the like the colored strip tests that you see on over-the-counter tests, where like there's usually a piece of paper, and this is the ELISA version in a well with liquid, but in a over-the-counter test, there'll be like a piece of paper that's got the antibody embedded in it. And then you pass the sample over, and if the sample has the antigen that the antibody is looking for, it binds. And then what comes next is the antibody linked to the enzyme. And then if the antigen is there, the substrate will change color. Okay. All right. So we have 2 things to talk about. So first of all, we have to talk about deadlines, and I just want to say this first for anybody who decides not to stay for the Kahoot, but Sunday is the review quiz for immunology, the final lab report deadline, and lab aid. Our 3rd unit test is on Wednesday, and there's no class on Monday. And then next Friday is the optional final, which I actually have opened as early as Wednesday for anyone who wants to take it early if they have scheduling issues. Okay. A reminder or a word to the wise, the lab report takes me ages to grade. So you do not expect this to be happening anytime soon. If you're waiting on this grade to decide if you take the final, you're going to probably miss the final. So if you don't like your grade right now, take the final. If there's any chance that you messed up the lab report, take the final. But with that said, the final is optional. You do not have to take it. Test 3 is proctored. So there will be backtracking, and you will have to come to Zoom, and all the usual rules will apply. And so if this timing of this test is not ideal, then let me know. Friday's optional final is not proctored. It is not allow backtracking, and you do not have to come to Zoom. So it'll be more like test 2 in that regard. Now, what we're going to do next is a Kahoot, and then I'm going to bring my baby on, but we're going to take our break first.
Question really quick. The final lab report, is that referring to the unknown ID?
Yes.
Okay.
Yes. Thank you for asking that. So yeah, we're going to take a little break, and then we're going to do our Kahoot. And then I'm going to bring my baby on so anyone who wants to see a baby can see a baby. And then it will be the end of class. There is, Renette, an extra credit evaluation. So basically there's an informal eval online that will be in the final module, weekly module, where you can say what you thought of the class, how you think it could be improved, what you liked, what you didn't like, what worked for you, what didn't work for you. And that's super useful for me. It doesn't go anywhere, like my dean doesn't read it. So you can be as candid as you like. And but I really appreciate the feedback. It's always helpful. If you like your study guides, that's because students asked for them. Okay, so you can make an impact for the next quarter. And I give you points for that because it's so useful to me. And I really appreciate you taking the time to do that. Okay, so I'm just going to pause the recording. We're going to take, I think maybe, yeah, we'll take our usual 10-minute break and then we're going to do our Kahoot. And I'm going to post in a minute here, I'm going to post the pin to log in so that you can start logging in before we really officially come back from the break so we can kind of get loaded up faster. But I will see you guys in 10 minutes. So don't go away, stay tuned. All right, we're going to get started. Here we go. Which of these is an example of natural passive immunity? That's right. When we get antibodies from mom in utero, natural passive immunity. Which of these is found on the surface of T helper cells? T cell receptor. CD8 is T cytotoxics, so it would be CD4 for T helpers. All cells have MHC1. MHC2 is only on antigen presenting cells. So the best answer is TCR. Parasitic infection associated with an increase in which of these? Eosinophils, that is right. Good job. A mutation in which of the following would cause the most serious loss of immune function? C3, the linchpin of the complement. This is a multi-select. Which of the following is required for T cytotoxic cell function? Select all that apply. All right, all of these except antibody binding to antigen is not required. Which of the following occurs during T-independent B cell activation? Only one of these that is required is antibody binding to antigen. Since it's independent, there's no T helper involved, there's no memory cells produced. Which of the following is not true about B cells? Yeah, that's right. B cells respond to one antigen, not different ones. We have different B cells responding to different antigens, but each B cell is unique to its antigen. Which of the following is part of the second line of defense? It is phagocytes. Skin and mucus are part of the first line. B cells are part of the third line. It's phagocytes that are the second line of defense. To grow a virus and create a vaccine for human flu, what could you do? You need a baby? Okay. Right, say bye-bye, baby. Oh. I know. All right, yes. You could inject it into a fertilized chicken egg. Putting it in medium is not going to work. Putting it in bacterial cells is not going to work for a human virus. So you have to put it in a chicken egg of these options. Which of these is a step in a positive ELISA? Yes, all of these. So you have to have your antibody binding antigen, and the primary binds the secondary, or secondary binds the primary, and then the enzyme that's linked to it cleaves the substrate. This is a multi-select natural killer cells. Select all of the true statements about natural killers. All right, so yes, they are using the same tools as T cytotoxics, but part of the innate rather than adaptive immune response. They target cells that don't have MHC1. They do not have antigen specificity. All right, multi-select. DTaP contains heat kill toxin and a protein isolated from pertussis. Which types of vaccines are in the shot? Heat-killed tetanus toxin and a piece of pertussis organism. What types of vaccines are represented in this shot? Toxoid and subunit, correct, not a whole agent. These are all bacterial diseases, and we don't use whole agents for that. But it's toxoid for diphtheria, toxoid for tetanus, and then the subunit for pertussis. Most effective type of vaccine in humans is typically That's right, whole agent attenuated, typically the most effective. True or false? Whole agent inactivated vaccine carries a risk of back mutation to virulence. Carries more of a risk of back mutation to virulence than whole agent attenuated. There's a word missing there. Is it true or false that whole agent inactivated carries more of a risk of back mutation to virulence than the whole agent attenuated? It is false. So the whole agent attenuated has a risk of back mutation. A whole agent inactivated has no risk. Our bodies produce all of the following immune proteins except not. Which thing is not produced by people? It's siderophores. Good job, you guys. These are bacterial. Interferon alpha and beta. How do they work? All right, they warn neighbor cells of a viral threat. Last question, what's C1 required for? It is part of the classical pathway. Antibody binds antigen, that recruits C1, C1 activates C2, C4, which activates C3, and all the things happen. The alternative pathway doesn't use C1, C2, or C4, just BD and P to activate C3, and the lectin pathway uses lectins to bypass the requirement for C1 and go straight to C2, C4. So classical, only one that requires C1. All right. Good job, you guys. I know everyone did great in the quiz today. Thanks for your participation. I'm going to end the recording here and then take any questions that you have.